I'd like to welcome Mike Müller from Python Academy, and he will talk about optimization in Python.
Thank you very much. I will talk about profiling, which is part of optimization, to be correct. Just a few words about myself. Some of you might know me. My name is Mike Müller, and I've been using Python for now about 16 years or something, if I calculate right, so it's quite a while. I was still version 1.5 when I started. And then 11 years or so, I gave my first Python course. And the last years, very intensive. I spent most of my time teaching Python or preparing courses or doing something around this, if I don't organize Python conferences, things like this. Okay, this is a talk about measure, don't guess, how to find out if and where to optimize. And I have the material here, so maybe you can find this link here. So I will put it up again and again. It's a Python Academy.com download PyData Berlin 2015. You should see this listing here, and there's one zip file there, and if you download it, you should get all the material. The presentation is about a 17-page handout and all the examples. I also have something about software. What software you need. I think I put it up, hopefully in the website, but you can maybe download something. It would be recommended that you work along. So I want to make it really a tutorial, not just a long talk where I'm talking all the time. I want you to do something, do something, also do an exercise, a few exercises in here where you're on your own for a few minutes that you can try to solve a problem. And that's typically the best. So if you do something, if you get your fingers moving. Okay, so let's see if I start with it. I will put up this download once you have your machines out, the download link again. First, I talk a few minutes before we're really going to start working together on these problems. Okay. The question is, how fast is fast enough? We work with Python, you want to have fast programs. And you know Python is a very high-level language. And due to this fact, it can be slow for some types of computations. Not everything. There are some areas that's actually pretty fast. But especially areas where you traditionally use languages like C or Fortran, Python is pretty slow. And if it's slow, that may be a problem or not. It's not really clear-cut in the beginning that slow is always a problem. And you can do optimization, but typically optimization comes at a cost. It's not for free. That's important. And the art is to find out, does it make sense to optimize here? Do I want to spend this cost? Is it worthwhile? That's a pretty tough question, maybe. And Python is very good in terms of maintainability. You can maintain it easily. It's easy to develop. But this comes probably at the cost of the speed for execution, because you have very easy to maintain code base compared if you write things in Fortran maybe or in C. But it might be slower. And this, you have to find the right balance. So that's a problem. But speed? You want to have your program go fast and you spend a week, or you don't mind, and in half a day you're done, and your program is a bit slower. It depends very much on your use case. And this is something you should take by heart. Optimization guidelines. Premature optimization is the root of all evil. And nobody really knows who said it, if it's Knus or Horry or somebody else. There are different sources on the internet that claim different things, so I said it might be somebody. But nevertheless, it's important. Don't optimize too early. That's very important. Okay, a few things before we start. First, you have to make sure everything's correct, and then be sure it's fast. So if you have a very fast solution but it's wrong, it's not really helpful most of the time. And if it's something slow but it's correct, it can be useful actually, even though it takes a bit longer. So make sure your program works correctly. And you always think about before you do something, think about the optimization, and especially make sure before you start optimization you have the right result. So make it work the way you want it first, and then think about making it fast. That's much easier than the other way around. Making it fast and then try to figure out where the problem is. So the price optimization I talked about, if you optimize, you pay some kind of price. Not always, sometimes if it's a smart optimization, which I try to show a few, it might even become clearer when you optimize. But that would be only a few cases. Very often you have to put some extra effort in there, and you might pay a price right now by paying more or spending more time on it. Or maybe later when you maintain it, or maybe you can even maintain yourself because there's some special things in there. You need somebody else or things like this. You need other technologies, need another compiler and all kinds of things. And in many cases, it makes your code longer and less readable very often, it could be. Again, more maintenance effort, and the readability might suffer when you do this. Yeah, so Python has very good readability, but this is maybe for the price it's a little bit slower, and you cannot have both. Not always can have both of these objectives. Okay, general guidelines for optimization. I have about 10 points here, which I want to make before we start. So make sure it's really too slow, which sounds a little bit silly maybe in the beginning, but think about it. Do you really need the speed? That's something is a question you might ask you again and again. Do you need more performance really necessary, or just because it would be nice? And maybe there are other factors like network traffic or input from users. Like if I write a GUI program, most of the GUI programs 99% of the time to sit there and wait for the user to click or press a mouse button or something. And if you wait fast or wait slowly, that doesn't really matter too much. When you wait, you wait. Yeah? And does it hurt if it runs slowly? If it runs overnight, if it runs in an hour or in 5 hours, does it matter? When you come in the morning, it's done. Maybe it's not a problem. So those kind of things. So that's very common sense, but most, I think, boil out to common sense in the end anyway. Okay. Don't optimize as you go, which is kind of, it can be alluring to optimize when you see something that could be optimized, but if you don't know, maybe you optimize the part where you spend only 5% of your time, and it doesn't make much sense to optimize this 5% of the time, make it 50% faster. So you save 2.5%, and the other 95%, you don't do anything. Because even though you might have experience and you might have a gut feeling, you can guess, you can be wrong. So I have some experience, and sometimes I have a guess, and very often I'm wrong, I'm guessing at the wrong place. That happens. So you want to measure, that's what you want to do. And only use realistic use cases, so you have to know what your software is designed for. So how many users you will have, for instance. If it's only for 3 users, you don't need to be too much concerned about performance. If it's for 30,000 or 3 million, there might be a different story. Yeah? And how often the program is used. This is a one-way script you throw away. It might not make much sense to put a lot of time and effort in optimization. Those kind of questions. So you can add more questions, but just be realistic what you want to do with it. And then when your program is slow, first think, it's really my program, the execution time of the program, or the other things involved. Like if you talk over the network, there are many other layers in there, and you can make a program faster and faster. It doesn't help, it waits. Or if you talk to the database, very often the database is a bottleneck. Call system functions, they might take time. The problem is, you might not know, and the answers to find out, you have to measure. That's something we want to do here. Next one, the architecture. The architecture can be considered like an algorithm in a higher level. It's like your whole setup, the whole thing, how you set things up. If it can run in parallel or something like this, conceptually, this is something you need to go through it. And unfortunately, there's no real recipe here. You have to really look at your specific problem and look if the architecture is right. So are there bugs? I still remember I'm involved in scientific Python, also EuroSciPy 3 years ago. This guy, that they had this Fortran program that's been there for many decades, and that they used it for this accelerator. And they said, okay, it has to be in Fortran, it has to be fast. And then they rewrote it in Python. Python is much slower than Fortran, isn't it? But then they figured out it had a bug, but nobody ever, because it's written Fortran 77 with equivalent statements, stuff like this, it's very hard to find bugs. And then the Python version was actually faster because they removed the bug. Yeah, so that can happen. You never know. So you have to be very careful with those bugs. If you forget to print an inner loop, makes things slow. Yeah, so the bug actually might be the bottleneck. Who knows? Suppose you do something again and again, which is not necessary, and you don't see it. Yeah? Because it's, well, so those kind of things you should also take into consideration. So, and now that's a core of the thing. If it's really too slow, now you've answered all the questions, so you went through and you slept a night over it, and you said, yes, it's too slow. And the first thing is you want to measure what's too slow. So actually you want to measure, and then you see when you measure before, and you measure after, you see whether you improved or not, and if it makes sense at all to do something. So you want to measure, and I want to show you a few techniques you can use to measure. And of course, you have to always check the results when you do something. The best is you have tests around. So you don't want to check manually all the time. So you want to make it automated. So tests means automated tests. So using some kind of a test framework, several unit test frameworks now. There's built-in Python unit tests, or PyData test is a very nice one, which is very low overhead. So for simple tests, you get started within 3 minutes, you have some tests. Yeah. And also try to cover most of the problems. So this coverage things means you want to cover all the lines of your code, or all your different problems. That's not a good idea to unplug the... Somebody stopped over. The projector. Okay. And then this, typically, if you do something, we touched a little bit on this topic here, typically the most you can gain when you improve the algorithm. So if you change the algorithm, you can get many orders of magnitude in speed. 4, 5, 6 orders of magnitude. If you switch from Python to Fortran, you might get 2 orders of magnitude, and then it's getting thin. You will never get 4 or 5. It's pretty much impossible. The best compiler can do it. But if it changes the algorithms, so we have to be aware of the algorithms, and you have to analyze a little bit. And again, measuring can be a good thing to test out different algorithms with different sizes of data to find out how this is going to scale when it's getting bigger. The problem is when the data is small, it doesn't matter most of the time. If it's getting big, then it really matters. And that's something you can do with the algorithm. And of course, nowadays it might be an option if you don't get any further, try to get a bigger computer. Sometimes just adding more memory might solve a problem, who knows. And memory is comparatively cheap, so if you pay a programmer for a week to work, you can buy quite a bit of memory. Yeah. Or also, if the fastest processor problem is, even now if you get a multi-core processor, you might be able to take advantage of it. As you heard in the morning, so doing things in parallel is not the easiest thing in the world. But still, that might be an option. Just spend a few $100 on some memory or something. Might help solve your problem. Okay, this is just my introduction. Now we want to do something practical. I'm going to use IPython Notebook. Who's using IPython Notebook? Yeah, most of the people. So I don't want to go into this. Just use it as a tool. If you don't, you can also use normal Python prompt, and also show you from time to time normal command line. Other question: who's mainly using Python 2.7? Okay, and who's using Python 3? Okay, so I have prepared 2 versions. I have a few tools. Not all of them work with Python 3 yet, but there are alternatives that work with Python 3. So I tried to make it work with Python 3. So again, please download from here. So if you haven't downloaded yet, please go here and download the material. This will be this presentation. And so, hope I speak enough. This presentation and a few small example files we're going to work with, and the bigger PDF with all this things in there. So it's about 70-page PDF. So I'm going to open the PDF, and we pretty much want to go through this thing. So this is a PDF you will find, and that should be kind of comprehensive. So because I wrote pretty much everything down, they should be able to follow along. So even if you get lost somewhere in between, you should be able to catch up with this thing. So, and hopefully everything works. Also, there's another document about software requirements in here, I think. Yeah. Huh? Huh? I thought I uploaded it. No? Of course, I have the software requirements somewhere. Somewhere up there. And there should be the software requirements in there. There should be a PDF with software requirements. I'm pretty sure I did it. Of course, it's not there. So just I upload this. If maybe you can download. I upload the software requirements again somewhere here, and then it makes it easier because then you can have the links. I don't have to tell you I have to do this and this and this. Yeah, it's not there, obviously. It's not here. Okay, I've copied and probably in the wrong place from the wrong place. Yeah. Probably the network broke down in between when I did it and didn't check that it actually finished uploading.
You use the beta house one, it's probably better than the inner space.
I have my own, so otherwise, because it always. Actually, I'm logged in this beta house, but still. So if you download now, it should be there. So if you download this one, it should be there. So software requirements. Yeah. So if you save it, there should be software requirements. Okay, let's get started. The first thing we go through this document. Actually, I have a paper that's easier for me to follow because I don't have to switch back and forth. So we go through this document here. Did you find software requirements? Did you download again? Yes. Okay. So go to the software. There's just some links. We don't know everything. We don't need everything at once, but this time it would be good to have it. First, a few things about measuring. There are a few benchmarks out there where you can actually measure. Okay, I'm gonna work with Python 2.7 and 3.4 and show you how this works with both. There are some differences, but I think it's a good thing that you know already how things work with Python 3. So therefore, oops. I use Conda environments. So I have a Conda environment for 2.7 and one for 3.4. So if you activate this one, so I would recommend also if you want to just make a new environment, and this helps. This would be 2.7. So it's an environment running in 2.7, and it makes sense if you work with it to change this tab thing here. So you could call it 2.7, so you can find your way through here. And the same, doing it for this one, activate the 3 version. So if you're not familiar with it, you can say conda create minus name, minus n, minus name, and create a new environment. So that's the 3.4 environment. Data. Source. Activate. Activate. To mean? Okay. Okay, now I'm in 3.4 and you are in 2.7. The first thing I would like to talk about the stones. Do you know the stones? That's the pi stones in Python. Pi stones. There's a benchmark typically used to measure how fast your Python interpreter is itself. Benchmarks are always kind of controversial. So if you use a benchmark, you can prove pretty much everything with benchmarks, or anything with benchmarks. But there is a... So I go in this directory. See. Why doesn't it go there? Okay, now I made a new directory here, and I have a directory for 2.7 and 3, and also you have the source. The source is what I just downloaded. Then you can see in the source there are some subdirectories. So I use this directory structure and it zips everything automatically. That's why that's kind of a deep nested thing. And there are several things in there here. You can have this PyStones. So you want to run the PyStones. And I think I didn't upload them. So the PyStones actually are typically located in the test directory. So if I run Python here, so if I don't know where the thing is, I write Python, and I'm at Python 3 now, and you can say import test.pystone or from test import Pystone. Why doesn't it do? Ah, yeah, I'm not using IPython. Sorry, I'm used to Python. Yeah. Ah, yeah. Sorry. So maybe I can just move this up here. So I didn't see this. Okay, I have to use IPython. That helps. So you use the IPython. So if you IPython command prompt can be interesting. So import test.pystone. Yes. And now as P, so just short. Now you have it, and you can actually figure out where it is because it tells you where it is. This is a Pystone file. This is where it's located in my case. Because you can use this Pystone, as I did, you can import it, and you can check your Pystones, or you can actually run it from the command line, and you can find it right there. So it should be there. Some older, I remember when you use Anaconda, some older versions didn't have it. Somehow they didn't put it in, I don't know why. But with 3.4 and 2.7, the most current, they have it. So now you can measure this Pystone. So if you have this P, and you have a Pystone, and then you can find out the Pystones, and it gives you the runtime and how many Pystones. Pystones is just a measure, so it's 71,000 Pystones. It's like currency here you can do. And the same thing you can do with Python 2.7 actually. This is just some arbitrary measure for benchmark. They're not good on their own. They're just good when you compare something. If you use the same benchmarks,
so is more better?
More is better. Yeah. The more they have, the better. So you might have a bigger machine, so you have more.
I have 76,000.
Yes, so you have a bigger machine. That's I think i3 or something, I'm not sure. So if you have a faster processor, it should be a higher number. Yeah, so this gives you some kind. Benchmarks are not really the best thing in the world, but there's maybe so far the best. You can compare something. Yeah, that's something. So that's one way of doing it, and you can run it from the command line. So if I just can copy this now, of course now I know where it is here, and I can just exit here. I just go out, and you can run this one from the command line. Just give it the full link to the Pystone, and now it's running on the number is a bit different. It's not exactly the same. You will never get exactly the same number. It can vary several % up and down. See? And you see it takes so many seconds to do 5,000 passes, and I get about 71,000 Pystones. And you can do the same with Python 2.7. You can check Python 2.7. The Python you will see, this is a Pystone 1.2. This is 1.1, but I checked it with the other version. There's no real difference. It's just maybe some bug fixes, but it's not totally different. So now, of course, I cannot use this one. I have to use the 2.7 version. And I'm not sure if I have a 2.7 environment here. No, I don't have it. So again, I can check where it is. I think it's in the root environment. Import test, and then you figured out where it is. The Pystone thing, and you have this. Normal test. Why is no module test? Interesting. Yeah, I make a new tab and I run my root environment, which is also Python 2.7. And that's the import test. Why is it not there? Because I did it and had it. Because there's a different version here. It's not exactly the same version as a Pystone 1.1. So it's good to name those things. And see, it is a 1.2, and it's a lib Python test. And it's not in here. But of course I did it. I don't know why it's gone. Huh? Da tut's. Ist es schön erstaunlich? Yeah. So import test, and it's 2.79. And I did it yesterday. I tried it again because I want to make sure those things work. And it's not working now, and I'm not sure why it's not working because it's just a standard Python distribution. But nevertheless, you can run the Pystone from here, and you will see a different number. And actually, the interesting one is when you run things with PyPy. So if I do the same thing with PyPy, I have a PyPy 3 installed now. I can use PyPy 3. That should work with the PyPy 3. Or you have normal PyPy, and I can run it with this Pystone. And you can compare it, and you see this is a bit faster here. That's not 70,000, it's 500,000. So it's a factor of 7, 8 or something faster. So if you use a PyPy 2, which would run with the other version, it's about 10 times as fast. I have some numbers in here. So you can compare the Python interpreters themselves, which may be interesting. This is but only for the benchmark. The comparison is only based on the benchmark, so it would be too much helpful for other things, but it gives you some kind of feeling for this benchmark, and all those big supercomputers are ranked by benchmarks, actually. Somehow, and somebody came up with benchmarks, and people designed those machines for the benchmarks. Yeah. Okay, good. This is about those Pystones, and I have also some small helper that can help you to use those Pystones kind of, if you want to compare runtimes on different machines, you can use this as a standard, and you can kind of normalize your results on different machines using the Pystones. There. Good. The first topic is profiling CPU usage. So there's two things. You can profile the CPU usage, and you can profile your memory usage. Both of them can be interesting. And the first thing is now, I want to profile the CPU usage. And to do this, actually, we start our IPython notebooks. IPython notebook would be the easiest thing to start an IPython notebook. And then I'm just check where I am. So I have made two directories. I make one directory point 2.7, and I start an IPython notebook for 2.7, and I start one for 3, because it makes it easier to work with it. And then we do some. So this is running with to 7 here. Nowadays, you can actually have two of them, two kernels with the same notebook, but sometimes it gets mixed up, so it may be easier like this. And we call this here Python 2.7. So it's easier to find out. That's the first thing. And we can do the same thing for Python 3.4. So I'm here now. And actually now I want to go cd source. And I want to, it should give me optimizing and then measuring. So I have a few of those scripts for measuring. They are in here. Is it big enough? Just take this off. So now it's my 2.7 is gone. So, okay. I'm here now. And the measuring, I have a few of those samples programs for measuring all those kind of things. And the first thing we have is a small, very simple. It typically makes sense to make examples as simple as possible. It still kind of catches the essence you want to prove. It makes it easy to understand. Otherwise, you have too many moving parts and you don't know what you're actually measuring. That's why I have very simple examples. So you can load them right here with the load. So if in IPython notebook, this %, if you don't use the % is a special IPython command. 1% always means for one line. 2% means it's valid for the whole, as 2% signs means it's valid for the whole cell. And you can have a multi-line thing in there. Now I load this thing, and this gives me call tips here. It's called profile me.py. And this is a very short program, you see here, which is very easy. I loaded it. Because if this first line was introduced by the IPython notebook, that's not in the file, but this is in the file. So you see, obviously, the file name. Because everything is also in the handout. If you look at the handout, you will find the same file name. So you can find them. Yeah, and this is one thing. I made everything work with Python 2 and 3. There are some frameworks doing it, but I didn't want to put a national framework here. They do essentially the same. The only difference here, I want to use range in Python 3 and xrange in Python 2. And one trick would be I check my version. So this version is a named tuple. .major gives me the version if it's less than 3. Yeah, so it would even cover for 1, but I've used 1 for in a decade or even longer. Though I said range to xrange. So in Python 2, actually I use xrange. When I say range in Python 3, range. They're not exactly the same, but for our purposes are good enough. Like range in Python 3, you can index, which you cannot do with xrange. But you can do everything. Like xrange has a limit of 64-bit integer, where range doesn't. You can use long for things like that. There are some small differences, but they don't matter for our purposes. Okay, and then I have a function, and they are very, very stupid. Actually, they don't do much. I use time, and it's just wait. And when it waits 1,000th of a second, it waits 1/10th of a second. That's all the difference. So I don't do anything. I don't use any CPU time, but I wait, which is interesting. Of course, you will see in a minute, you can measure different times. You can measure what's called the wall clock time. This is the time that actually elapses, so like the clock at the wall. Or you can measure CPU time, that's actually CPU time that's spent. So that's two different things. And because this sleep doesn't use any, or very little CPU time actually, or no CPU time really. And then I have two that just use them. I can use these two functions. I can work with them. Okay. Now there are two ways of working with this profiling. You can do, the IPython notebook has a special command called %prun, which is kind of mimicking the built-in profiler, because not everything with a built-in profiler works. Actually, talking about profiler, there's a module called profile. It's written in pure Python. It's pretty slow and has a lot of overhead. And there's one hotshot, which is actually pretty good, but it's somehow not supported anymore, not recommended. And the obvious choice is C profile. The last years, everybody is doing everything with C profile. C profile is part of the standard library, written with the lowercase c and uppercase p in Python 2 and 3. So they didn't rename it, so it's called C profile. And this is a tool that helps you to find out how much time you spend in what function. So it's purely on the functional level, so you cannot go deeper. We will see the other tools who do this. You can find out how much time you need to work with a function, or with one function or the other. You can do this from here to a certain degree, not everything, but a few things you can from here. Otherwise, you have to use prun, which is doing pretty much the same. So I say import C profile here. Just go along. This makes it easier and faster when I do this. Import profile me first. Yeah, I don't. So there are two ways. I could import the script. They have the full name. If I just execute it, will be in my namespace. This is fine now. So because I loaded the whole thing in the cell and execute now, the function fast will be in here. So I can use, say, let's use fast, for instance, and it would be here, and it would do something which is just using up CPU time, which is the purpose. Yes, I loaded this module. That's the line I typed in, load profile me. So I've been in the directory optimization here, measuring. So if you download it, you find the source, and you go to measuring, you find a bunch of those scripts, and you can use all of them actually. Good. And then we have the C profiler, and that's a standard way of doing it. Actually, if an IPython notebook, typically use prun, because prun gives you pretty much the same functionality. It's a bit more convenient. But sometimes you want to measure when you're not an IPython notebook. If you want to run something on a machine, there's no IPython notebook, you want to run longer and you're not interactive, then it's always good to know how C profile works. So I say import C profile. Yeah, see, if I press tab, I get call tips, and there's two C people in profile and Python 2. That's why Python 3 sometimes some libraries in Python 3 are renamed. Because typically that's not a good library name. Library name should be all lowercase. That's PEP 8. But those things are very old, and that PEP 8 is from 2002 or something, and this predates PEP 8 already. So nobody cared a bunch about how to name those things. Okay, and then I can make let's say a profile, and I say this is an instance of this class C profile. C profile is lowercase, is a module, and profile is a class. The profile is spelled property. And this profile offers several things you can do. And you see this profile dot tab gives you quite a few things. You're not going to look at all of them. You don't need all of them most of the time, just a few of them. And one of them would be run call, which is a simple one. Run call, and you can use run call, and now you can put in like use fast. Yeah, and this would run use fast without the arguments here. You can also supply the arguments, and you get back. Yeah, now the profiler has run. Actually, I say profile. Profile is strange because the module. I made a mistake. Profile is the name of the built-in library, so it's better to call it profiler. Just to, naming is kind of important. If you mix up the names later, you try to do something and it's not there. So profiler, and now the profiler has several options, and one of them is called print stats. Print stats. Yeah, right there. Print stats. And this gives you statistics. So you can get statistics. Now it's looks a bit strange because I have this blown up font here. But it gives you statistics and tells you what function's been called how many times and how long it took. So this is very simple. If you have a real program, you have hundreds of thousands of function calls out there. But typically they are sorted in way. Most of the time you're only interested in a few of them that take up the time. If all of them take up pretty much the same amount of time, it's getting difficult anyway to optimize. If you find one or two that takes most of the time, then it's obviously the target where you want to optimize. And finding the things is important. And the problem is when you measure, things can go wrong when you measure. That's very important. So if something is very strange, then you might want to look at a different approach of measuring. The problem might be the measuring, not your program. It happens. Especially if the time is very fast and your measuring has overhead, then the overhead of your measuring might be more influence the whole thing than the execution of the program itself. And that can be a tricky thing. And it's really difficult to find this out, because then you might chase something which is not there. So you can see you have the number of calls. I have it written here somewhere, but it's all is, yeah. The number of calls, the total time, and this function then it's divided per call. How much is per call? It's so small that it's 0 in this case here because it's only 3 digits in seconds. And the cumulative time. And then you have the file name here that tells you where it is. So since I'm interactive here, it is interactive interpreter. Okay. I have more things that you can do, but for this one, that doesn't really work here in the active thing. But you have this p-run. And this p-run, so this is magic. IPython is full of those magic methods. And if you don't know, always use a question mark and tells you what it's doing. And it tells you, OK, that's how it works. That's how it works. So you say p-run. And p-run is equivalent to using the profiler run. Now we used run call, which is a bit different from run. Run would... See, run call is you provide the function here as a function object. If you use run without the call, profiler, run, then you have to give it as a string. Then you have to give it as a string, and you call it something like this, I think, and that gives you back this profiler object here. And then you can work from here. If I now call just a p dot print stats, gives it the same. So for this it works. There are a few cases it doesn't work, but you can achieve the same thing using the built-in %p_run. So %p_run here, and then use fast gives you the same option, and this one you just call it, and now it gives you the same call here. So now you can see this use fast is this where I call this function, and you can see that most of the time is spent in the sleep. I'm sleeping per call, I'm sleeping this 1,000th of a second, and I call this 100 times, and there's pretty much 0.1, and the rest is just all the overhead of all the other function calls that are there. Yeah? A function call in Python is relatively expensive, because very often there's a lookup involved and stuff like this. So function calls are typically expensive compared to C or other languages. And now I can do the same thing with use slow. Here, use slow. And I call it, and then you see it different. It takes a bit longer, because that's why it's called use slow, because it has instead of 1,000, I wait 10th of a second, so it has to be 100 times as long. And you can see now it takes 10 seconds in total, and most of the time is spent to sleep. Yeah, see there, the sleep here, down here, and 0.1, and the rest is kind of overhead. But this is the one that actually where you sleep. When you have 10 seconds in a little bit, yeah, that's the time you sleep. So this is a very clear result, so you can see what's going on. So, and if you use Python 3, this should work with Python 3 the same. So I tested everything with Python 3 to make sure. And in a few scripts, I put a few things in to make it work with Python 2 and Python 3. That's always a good idea. If you write something nowadays, you still have to use Python 2. Write it the way it runs with Python 3 and test it. We'll thank you later. In 5 years, support for Python 2 runs out. That might be a commercial company taking over, but still, Python 3 gets a lot of new and nice things you won't be able to use with Python 2. So going to Python 3 is something you should do soon. So, and now with this p-run, you can do a few things. Like, assume you have a real-world case, then you have a lot of output, and you can limit the output. Like a few things you can do with the p-run. You can say -L. I want to have only 2. Use fast is easier, now it gets faster. Now when you have 2 lines of output, you can only 2 lines of output. It tells you here, list reduced from 5 to, this could be like 5,000. You don't want to have 5,000 lines, it's typically not useful. And you can reduce the list of lines. So this p-run takes a bunch of options. And one of them is this limit, -L or -L. Yeah, minus. And you can also say, I want to use only fast, so you can provide a string, and then it will only show the ones. That's not nice because it's from this. Use fast here, and now it shows only the ones. You see, a reduced list from 5 to 2 to the restriction fast, so the name fast has to be in the function name back here. So there are many ways to filter those things, which is a nice thing. The nice thing, you don't need all of them, but a few of them can be really useful. So use fast can be one of them. Okay, you can also create a pstats object. It's the same thing we had before. So this stats object, which can be used to do some manipulations, because those things, they can also return something. The percent can return something. In our case, I can return this pstats object, prun, and do the same thing. I have to say -r to make it to return. So there's options, yeah. And you say use fast, and then you have the stats object. So it's showing the result. If you don't want to see the result, you can suppress the result. If you don't want this popping up all the time, because now we have object to work with, you can say -q, like quiet. Yeah, and now it's suppress the printout. So it can be annoying if it's a lot, so printing all the stuff. And now we have a stats object, and you can work with the stats object. And this one, you can do a bunch of things. Here is a stats object here, and I have a few things written down what you can do with the stats object. And you have this here. So the stats object here, this goes back to the, it's because it's the same as with the command line. Yeah, you can, for instance, sort by things. So now typically it's sorted by time. You can say sort stats, sort by something. Sort stats, and now you can sort it by the number of calls, for instance. So calls, and then you get a new object back and you say print stats. So this is the same thing as standard, but you use prun to generate this object, and now you see now it's ordered by the number of calls or rather by the time. So there are a bunch of options what you can do with it. You can sort in all kinds of ways, sorting by calls, sorting by time. So I can do the same thing. Instead of calls, I say time. Yeah. So this case is pretty fast. And now it should be by time. It's giving me the same output. Yeah, this is the most of the time. And here, it's just by coincidence the same now, because my example is so short, but it's supposed to be sorted by time. And you can also have find out who's calling whom. So you can say callers here. So you can say print callers. It's this thing, probably not sort print callers. Then you can find out who's calling whom. Print callers or callees, which way around you want it. And you can say like fast, and then you figure out who is called whom. And you see now you have this relation with these arrows. This here, this is called by the other function. This is called by the other function. So you have these relations, you have the functions. And yeah, and you have the calls. You can also say, can reduce it too fast. And if you don't have this one, there should be everything. Yeah, that's everything. And you can see who is calling whom. And it's a little bit strange to read because it's designed for a wider screen on my screen. So good. There's a few things you can do, a few statistics you can run on. And this is nice because it works on the command line. We will see in a minute there's also a bunch of tools that gives us a nice graphical output. Yeah, which can be very useful because now you get a big table with numbers and you have to look through this table with numbers yourself. But there are some tools that help you to work through. So if you want to do the same thing, that should also work in Python 3. There shouldn't be a difference, so the time should be the same because now it's spending the time anyway in my sleep function, but there shouldn't be any difference. Anybody working with Python 3 now? Yeah, so you have the same result. So if you work along, if you see a difference, please say something, then I might be able to explain if there's a difference anywhere. It's not supposed to be, but sometimes I might have forgotten something that's different here or there. Okay, I talked about what's called wall clock time and CPU time, which is a very important topic. And I have another script here. And this is a script, yeah, which one is it? I didn't write the function name in here.
There was a difference in Python 3 with calls. What do you make in 3? Was it the previous one?
Yeah, then I had calls here?
No, call. Yeah, yes. Yeah.
I overrode it, yeah? So?
That one. sort starts. Okay, maybe.
Yeah, so I order by, you see this one, they have, both of them have 100 calls. So if you want to get this thing sorted by something, you can also use prun sort that offers a sort command. You can say prun, so prun offers more. You say sort by calls and then sort by something else. I think I have to put it in strings, make it a string, when I'm not mistaken. Here, you can sort it with calls and time. So you say by calls first and then time. So you can have multiple criteria, use fast. And then it sorts it accordingly. Yeah, so it is. You don't see the command line. This is a line. You say sort by calls first and then by time. So this is called first and by time. If I move this, if I switch this around, hopefully it should see a different order. Oops. So there. And now you see, now I have this function sleep first here, and then the other function fast. And if I do this, it should be the other way around because the time is first and then, no, it's by incidence. Yeah, it's the same because the other one was also sorted. Yeah. I cannot prove it, sorry. I have to think out how to prove it. But now it's sorted by time first and then by calls, if you want to do this. And also you can do a few more things. You can actually export the results. And there are two ways of exporting the results. The one way would be exporting the results. So if I now use always quiet, so it doesn't print everything. So I say prun quiet, and I say t, and this t exports things to the to a text file here, and then everything is, if it's big, might be a good idea not to show everything in a notebook all the time. This notebooks, if you work a while with a notebook and you have like 400 or 500 of those numbers there, they get very slow, at least for me in my Firefox. It's kind of suck up all the memory. And so I say starts, and I use fast, and here you have this. Now, you see now it's written to this file, and if you look in the file, which you can do with less here, so it is. All the commands I use should work with Windows also. If you use Windows, you can use ls and less. They are mimicked with other. They're just built-ins. Yeah? Actually, this less is supposed to be the less with a %. If you don't have to find a name less, then it works. If you have one, you have to use a %. But see now, this is inside the file. This is exactly the same output we just had. There's another option, and this other option would be I can save this in the stats file, and the stats file can be used later with other tools. So as instead of saying T, I say D, like dump. Yeah, dump. And it is the same thing, and I say fast dot stats, maybe. Some call it perf, some stats, doesn't really matter how you call it, it's just if you're consistent, it should be fine. And say I use fast, and I can save it. And now it dumps. And I didn't say the quiet flag, though it prints output. So if you say quiet, then it doesn't. So it saved it there. And this is something, so you see it uses Marshall. Marshall is a bit simpler than Pickle. It's a bit faster. It's not designed for human consumption, but it can be used by other tools. They can display these results nicely. That's what we do in one of the next steps. Can you follow along? Is the speed okay? Yeah, so it was important. If you do something, it might be more useful for you later because you might remember, I suppose, when I talk all the time only. Okay, the next topic is the wall clock time versus the CPU time. And for this, I have a script here and clock check. It's called clock check. And I just look inside. Clock check looks like this when you type it right. So I look in this clock check here. I load clock check. And this is something you can check because if you use a Unix system or Windows system, things behave differently. So you have the same name of the function, but it's doing a different thing, which is not very nice. This is not especially due to Python because in the beginning this library is just a thin wrapper around the C library, and they have the same name for a different thing. There. Okay. Okay, I do again from future input print function, which gives me the print function Python 2, some imports, and time it. Time it is the tool of choice. So if you do any timing, always use time it. Never use time, the raw time, which is very low level. Just time it has some high abstraction, which is much safer if you work on multiple operating systems. Okay, then again, this Python 3 thing. And see, now we have different ways of finding out the times. There's something called OS, the operating system module OS times, gives you a long tuple of times, and that takes the first one. And the first one is always the CPU time. And then I use time clock. And the interesting thing about time clock means on Unix, it's just a timestamp. And if you do time clock here and later, and you calculate the difference, you know how much time elapsed between them. And, sorry, on Windows, that's on Windows, and Windows is a timestamp, whereas on Unix, it's a CPU time. So it tells you how much CPU time elapsed since the first call. It's a very different thing, yeah? So the wall clock time it's a real time that you spend running the function. As you see it, especially if you use sleep. If you say sleep a second, then the wall clock time is 1 second. The CPU time is next to 0 because sleep doesn't do anything. If you run a program in parallel, so if you use a different program that doesn't have the GIL, you run it in parallel and you run it in 4 processors, then the CPU time can be 4 times as long as the wall clock time because you use much more CPU time. You use 4 processors than the wall clock time. So sometimes if the CPU time is longer than wall clock time, that might be indication that you run in parallel, unless you have a measuring error somewhere. Who knows? Okay, that's what I'm doing here. And then I use default timer, and the default timer is doing the right thing. So if you want to do this default timer, it gives you a timestamp. It works in Python 2 and Python 3. Python 3 gained a new thing in the time module called perf time, which gives you pretty much the same thing as default timer. But default timer works in Python 2 and Python 3. And it's just the perf time in Python 3 anyway. It's just the alias. And if you do this, and then you can run this and you can look. So anybody has Windows? Yeah, so you see some different results. So it's kind of exotic here with Windows. This one you can run from here. You might be familiar with if name equals main check, which is run if this run main. A notebook is main, that will be run as. If you can run it from here, you can run it from the command line. And you will see numbers like this. And you can see here, if you run a Windows, you should see more digits. This is actually there's a CPU time, but it's very, very coarse on Unix. Yeah. Only 2 digits. And this is this time clock, which gives me the same thing here, CPU time. And this is a duration, which includes this 1 second. Yeah, this essentially does. This should be pretty much the same. It's just some error here. And here you see this plus 1 second because electric time. If you do it in Windows, you should see some different numbers, a different distribution somewhere, because then time clock should give you this thing. The default time should be the same, but time clock should show you 1 second, and this one should show you a few more digits here, and this is it. So you have to be very careful if you go to the internet, you go to Stack Overflow, paste something in, they use time clock. It works on Unix systems, and you use it in Windows, it doesn't work the other way around. You get some totally screwed results. So rule is use default timer, and then you're on the safe side, then you know what you're measuring. Very important, otherwise you measure and measure and measure, and you don't have doesn't make any sense. And then a day later you realize this problem is your measuring tools what you're using. Okay, I have a small tool here for measuring CPU time. Load CPU time. That's something I wrote. So I've been giving this kind of tutorial for several years, and this is something that came up in one of the things. So again, I do the check Python 2, Python 3, have C profile here, and I check the platform. Typically, you can say this platform Win32 should be Windows platform, some kind of. And then I use here for the CPU time, I use OS time, which gives me this tuple, and it takes the first entry, which should give me the CPU time. And all other systems I know of should use time clock. So I don't think there's anything else in Linux and Mac around. Other more exotic systems, I have no idea, but those systems are covered. And you have this one now, if you run this, then you have a reliable CPU time measurement. So you need to do some tooling, and you have to be aware of this. And this should work. And here I just do this sleep. And here I do a loop 100 million times, and then you should see a difference, because this should just use wall clock time for 2 seconds, but no CPU essentially. And this one should use both CPU and wall clock time. And if you do this, and you run both of them, and then you print it out, and I make this profile on print the stats before and after. And the thing is, this profile takes an optional argument, and this argument is a function. In Python, everything is an object, including functions, or some people say functions are first-class objects. In Python, only first-class objects. So you can provide a function here, which is kind of a callback. So this is using this function. If you don't do anything, it uses the normal timer, which gives you the wall clock time. But you can provide your own time. In this case, I provide my CPU timer and measure the CPU time, which is a different thing. Yeah. So if you measure this, they should, after a while, it takes a few seconds because it's sleeping and doing things, should give you some results. Is it running? I think it's running. Yeah. So if the star here is running, it should give me gives me some results. And you have this two, and the first one is a normal one. The other one is a CPU count. You see, they have this 2 seconds wait here, and the other takes time, and here is 0. Yeah. No 2 seconds wait. It's so fast that you can't see anything. Now the others are faster here. When you measure both of them, 2 and makes 5 here. If you take 2 off, it's 3.6 instead of 5.6. So it's important. You have to know. You want to know the wall clock time. You want to know the CPU time, and these are some small things that can help you actually. Good. So this is about the tooling. I would like to show you some more tools that actually are nice to visualize the results. And to do this, I have a few more, a little bit more complex examples. So it's not everything that simple, because our functions are very, very easy here, and have a little bit more, not much, but a little bit. And let's have a look at them. So yes, still in the measuring directory. If you go to the directory algorithms, you can go up a few directories. Optimizing algorithms Pi, is it called Pi? No, not algorithms. So it's Pi directly. Yeah, so how to calculate Pi? You might be familiar that this prime example calculating Pi with Monte Carlo, which is a very stupid thing, but takes a lot of CPU. So that's a good example to show to do some profiling. So I have two functions, which one is called simple Pi, the other one is called numpy, which is the function I want to use because they do a little bit more and get a bit more interesting. But still okay, not too complicated, otherwise it's here. This is the function. I don't need to explain too much what it's doing. It's using two random numbers to find a random coordinate, and then checks if there's random numbers within a circle, which is using the Pythagoras. So it squares x squared by y squared, and the root out of it gives you the distance, and you know where it is, and then you can figure out if this point is inside the circle or not. And depending on this condition, you count it or not. So if it's less than 1 inside the circle from 1, then you increment the count. And this is a very stupid method to calculate pi, but you have to get a very high number of n. So this total here has to be a few hundred million or billion or something to get something that's kind of 2 close to pi. So if you want to have 4 digits, you want, so maybe a normal machine, it will take many years to get there or something. Yeah, so I do this with a million here. And then I just run this. So now I want to actually analyze this one. This is just one helper. I'm not doing it here. I'm doing from the command line now because I want to use a few tools. And there are different tools. One of them is run snake run, which is Python 2.7 only, and I don't think anybody's working on it right now. It's kind of a bit dead. And there's another one called snake whiz, which is more modern, which works in Python 3, which is nicer. They look a bit different, but that can be interesting because those pictures, they're not only nice pictures. They're really useful because they give you new information. But again, look at the other one. The other one is using NumPy. NumPy called here. And it's doing actually the same thing, but it's using NumPy. Most of you will be familiar with NumPy, so instead of doing the loops, I do it without the loop. Huh? If you work with NumPy, you never write loops. If you write loops, NumPy, you're doing something wrong. So you say random rent, you get a random number. Here, between 0 and 1, and 1 here, this is, instead of doing the loop. The disadvantage is you have to create those arrays in memory. With the other one, you can make the number as big as you want. It takes a very long time, but it works. Here, you reach the memory limit and you get the memory error. If you make it too big, you get a memory error. Yeah. Some operating systems, they swap, but they get so slow that everything stops. Yeah, and then do the same thing and do square root on the whole arrays and get it back, and it gives you the same thing. It's much faster for these numbers than using the Python loops, because it's moved to C loops. For this thing, you could even use something like num expression, because it's like polynomial kind of things. So, yeah, I think you could, to a certain degree, use num expression, make it faster. And then you do this count inside, and it just takes the length of this. Yeah, say at a distance less than 1. There are different ways of doing this. I think that's the fastest. Okay, these are these things. And now, actually, what I'm doing, I create stats files here, which give me this is the same thing we just did. And the stats files can be used with other tools, with this nice visualization tools, to make some nice pictures. So I go to the command line, and I create these, make a new tab. And when you want to use run snake run, if you get it to install, so you might not be able to get it installed that quickly. Then the problem is run snake run needs WX Python, and then when you run it from inside a conda environment, it tells you cannot for some reason. I have no idea why, but it doesn't want to do this. You have to run from outside. But still, so I'm here, and I'm go to the sources and go to Py, and now I can generate. I can generate the stat file as we did inside, but you can also use it from the command line. You say Python -m. You can always run any module from the command line without importing it. And you say module C profile, and now I have to look it up. It says -o, and -o is the output. Yeah, C profile, and you say -o. Simple py.stats, and then you say simple py. Now it's generating the stats information for us, and you can do the same thing with NumPy. NumPy stats NumPy. So, and this generates. And just print something, this generates this two stats files. And these stats files now can be used with these tools here we have. And I want to show you two. And the first one is run snake run. Once you get through all this very installation process, it installs with pip. And you can also install WX with pip, I think, or at least with conda. If you have a root environment, it should work. So in the root environment, I'm a root, I'm not in a virtual or conda environment. And now if I say run snake, and the name simple py.stats, and if you do this, it should hopefully after a while show up, and right there it is. You see now it has the same table we had before, which is longer, and you have these boxes, and these boxes represent the functions. And you see outside is a function that calls everything, and then other functions inside that call the other ones. And if you look carefully, you find this is called a random. That's called the mass square root. Yeah, and this is the whole simple py function called here. So that's something you can do with run snake run. You can inspect it, and of course, if you go in here, it gives you the function, all these details, and you can do more things here. And you can look at the different functions here. Yeah? You see the functions, who's calling whom. It's not so difficult here because it's a very easy setup. I close this and do the same thing, but now with with NumPy, and we see NumPy will be a bit more involved. And now you can see, so typically, what it means, if you see a big block with a lot of color, that's the way we have to go. If a lot of small blocks, it will be hard, because you have to get to all of them. And you see, this is NumPy, and NumPy is doing a lot of things behind the scene. That's why you see all those little boxes inside each other. And you have some overview of what's going on. There's not so much room to improve too much inside the NumPy boxes, because you would need to change NumPy maybe if you want to do something. So unless you change your algorithm in a way that you use some other functions that might be faster. But this gives you a nice overview, and you can go there and find things out. This uses WX Python and Square Map, so it's a few things you need to install to get it to work. But there's another tool, and the other tool which I would like to show you. Are we supposed to have break already? When is break? Okay. It will be hard to do this, but I'll show you one nice picture, and we can do more after the break. Snake Wiz is called Snake Wiz. Snake Wiz. Okay. And now I say simple stats, and I can run it through, and this gives me this picture, and that's pretty much the same thing as run snake run, but a different logic. So in run snake run, we have the outer function outside. Here we have the outer function inside. This is the main function, because it takes up the whole space. And this function calls the other function outside, yeah, and you can see how much time they take up from here. So yeah, that takes a bit. So if I go in here, this is this function, and if I click on this function, this is just some help or just some exec or something. And this function, if you go in here, you see this is this function that takes its own time plus calling other functions. This is calling this function. This is a function. This is the time it uses for the. If you go in here, you can see it. So this is a function. Maybe if you look in the source code, this is a function simple. This is a function pi. This is this function. This is this total function. And this function is a function random, and this little one is a function square root. You see? This one is calling random here, and it's calling square root. And it tells you how much time it takes up. This is how much time this one takes up of the function, this one, and the rest outside is how much time is spent here and here doing all this calculation. Because remember, the courses level, the finest level you can get down is function level count. So function level, there's no function calls here, that's why everything is together. And this is pretty interesting thing. So this is random, this is square root, and the rest is what happens in the function itself. That's why it looks like this. And you will see this then, there's something missing here, because if you have different ones that go up, because there's nothing left anymore, and you have this kind of thing. If you don't like this is called sunburst. You can go here and can change it. There should be, is it something wrong with my solution? There should be a way to change. Yeah, wir machen Pause. Okay, we have a break first, so in the break I can figure it out, because there should be a way to change the display. After the break we have finished this nice color pictures, and then we have something about memory measurement, which can be maybe interesting. There are some tools that are not as common as C profile, likely. So there are still a few people coming, but you can maybe continue with some questions if you have questions, so that are maybe just interest for you, not so for the rest. But you just realized that some Python 2.7 installations don't have this test, which I figured out myself. For some reason, I'm not sure why. It's supposed to be there. It's a standard Python from Python.org. It's supposed to be there. If you have a different distribution like Anaconda, the older Anacondas, they didn't even have tkinter sometimes. So that might happen. But you can find it. It's just, you only need to copy this PyStone file somewhere. Actually, I plan to include it in the download, but I forgot to put it in my script and didn't zip it in. Yeah.
I wasn't able to install PyStone
Yeah, that's what I just said. The Python is not there. If you Google for it, you will find it. So I have about 7 different versions on my machine somewhere, but not they're supposed to be that you can find it. And there's a Python 1.1 for 2.7 and 1.2 for 3. So but I checked, there's no big difference. It's just some bug fixes and some things, I think. Okay, maybe I continue. We had this tool here, this snake whiz, and I just realized I also used the old version. So you have this what's called sunburst. When I showed this is a sunburst setup, and if you change the setup, you can have an icicle here, and it's a bit different. And you see, this is the outer version now, which used to be the inner circle, and then going outwards here, and you can see this how this is distributed. You will see the same colors as when you go back here and send it to sunburst, which should give you this layout. And there's a few things you can limit the depths. If you don't want it that deep, you can have 3. Then you only have 3. And you can cut off like very short functions. You say they are shorter than 1,000, then the biggest one, they won't be shown. Because some pictures cannot be displayed. If you have 100 million circles, I won't be able to display 100 million circles, obviously. There's a limit to what can be displayed. And you can also click, so if you click on here, then this, which is highlighted now, becomes the inner circle. Now this is the inner circle and the other ones, so you can kind of zoom in. It takes a while to get used to this display, but it's pretty interesting because it gives you quite a bit of information. And you can also go to the call stack here, and it gives you, for this, it's small here, but it's a call stack, you can see this function called this function, called this function, called this function, so on. So it's quite a bit of information. And of course, you have the table down here. This is the table, so if you want all the raw numbers, they're still here. Yeah, so. Good. So this is a snake whiz, pretty interesting. And there's another one, it's called cache grind. But I couldn't get it installed. I could install cache grind, but it didn't work together with graphviz, which is needed to make this graph. So it's pretty difficult to install, and so I just skipped it. So it gives you another view on it. But I think the snake whiz is pretty good. And it's a nice approach to use a Tornado to actually run the server. So when I started from here, that's what I did here. It starts a Tornado server. You might, or Tornado, I think Tornado is American. That's the same server IPython notebook uses. It's pretty fast server, and then produces this, and everything is JavaScript here. Oh, it's a pretty nice project. Good. This is measuring CPU. So it's an interesting topic to measure CPU. And now you can also, as I said, we are limited to functions. When I do something, we are limited to functions. And as soon as something happens inside a function, that gets problematic. And that's especially problematic here when you see NumPy. You see, inside this function, I don't have any breakdown except the random calls. But sometimes you want to see more what's happening inside those functions. And which line of this call takes up the most of the time. And this is done with a thing called line profiler. And the line profiler is a tool. Yeah, I forgot one thing. The snake whiz also has you can load an extension in IPython notebook and run from IPython notebook. Gives you the same picture, but you can run from here. So line profiler, you can go line by line. You need to install it, and it's called kernprof, and you can profile. You can profile the function. I do it from the command line now. Here, I go to the command line, this 2.7. I exit. And I say kernprof, it's installed, I should work with kernprof. And I just say, check where I am. I should go to the PyData optimization. No. Source. It's called source. CD source. Source, optimization, measuring. And if I say kernprof, there's a profile me, for instance. I have an example here, profile me. That's a thing we looked at before with a fast and slow function, then it will give the text a little bit here. Because this one works just as a normal C profiler. And I didn't set the option minus dash v here, so it doesn't do anything. You have to say dash v for verbose, and that gives you the output. So it takes about 10 seconds, and you see the output. So it is the same thing as a C profile, so you can use it as a replacement for the C profile. But you can also do something with it. You can actually put profile in with a line profiler. So if I did this with a line profiler here, I go to measuring, and I say load profile me line profiler. That's pretty much the same thing. The only difference, I use a decorator. Are you familiar with decorators? The decorators are the thing with the add sign, which is actually, this is just a function that's doing something with a function. What is doing it, you don't need to know the details, but it's changing this behavior of the function. In our case, it adds line by line profiling with this function. And just put profile here. There's no import, because this one is not supposed to be run in the program, but run through this current process, because there's no import profile or anything. I will show you in a minute how to turn this off. And now I can do line by line profiling. I use the same thing. I say verbose, but also minus L, which means line profiling. And then I use profile me line profiler. What's the name of this thing? Use line profiler. Use line profiler. And then it takes also about 10 seconds, and then it takes even longer because it's doing more work. Now it has quite a bit of overhead and gives you a line-by-line breakdown of the thing. This is the output, and tells you line by line how long things take here. In this case, see, it gives you all this for all these different things, line-by-line breakdown, and say, okay, 99% of the time is spent here, and only less than 1% in the loop. Then you know where the time is. Whereas here it's even, because it's slow, there's 100%, because there's a resolution of 0.1%. Okay, let's look at a little bit more interesting case for this one. I have one called accumulate. I just load accumulate to show you how this looks like. This is a very simple function here. You see, I get an iterable. So iterable is anything a list, or iterator is also iterable, anything you can iterate over. You can write a for loop. And then I take the first element of this iterable here in this case. In this case, it needs to be indexable, it has an index. I get the first one, and then I go through the rest, so everything from here to the rest, and just takes the old value here, and then the new value would be the old value plus the new. So you have this, and there's actually in NumPy, if you say NumPy add accumulate, it's doing the same thing, if you know this. You accumulate the numbers, so if you have this input, you get this output, yeah? 0 plus 1 plus is 1, 1 plus, there should be a 2 up here. No, 5 here. So this starts at 0, 0 plus 0, 1, 1 plus 2 is 3, 3 plus 3 is 6, and 6 plus 4 is 10, yeah? 0 to 4 is numbers, and so on. That's accumulate, so you see the accumulation. Okay, we don't want to go into the details what it's doing, but we want to profile it, so I run it through the line profiler. And then I can just use the same command here, accumulate, and you see now it's a bit faster, but now it gives you a breakdown how long things take. So it's easier. You see, now I spent about 23% here, 26% there, and 23% there. So they pretty much take most of the time, and the loop itself takes about also 20%. So it gives you some rough numbers, and you can see where the time is. And potentially what you can do, because now you might see, oh, maybe I can change something here. Maybe that's a problem. I did something stupid, and I could change it in one way or the other. Okay, a few other examples that give you a little bit some taste what you can do with the thing. One is called calculate, and this calculate here actually is just doing a few stupid calculations. So I do different things. I say x is number plus 10, number times 10, number to the power of 10. And then instead of using this literal power, I use a built-in function power, which doing the same thing. And I use mass square root, using explicitly mass.square root. And here, you can also do something like this, make it a local variable, and use it here. And just, this is a calculation, it's just the access time. Just some things you can do to see how much influence things, or how long things take. And this can be pretty interesting. You get a feel for it. It takes a bit longer. And you see now, the power takes much more time. If you multiply something by 10, it takes 6%. Taking something to the power of 10, of course, takes longer. Much more complicated operation here. And the square root takes so much time, and it doesn't really matter. It's a bit slower when you say mass.square root compared to square root, but not much in this case. Yeah? But you get the feeling how things work. That's something you can do. Yeah, and then I have another one about local references, which can be optimization technique when you local ref. So local references. See what I'm doing here? I do things. I make a fake profiler. I try first when I run under current prof, then this profile exists and it works. If not, I get the name error because the profile doesn't exist, and I define my own decorator. And this own decorator doesn't do anything else but taking the function and return the function. So it's kind of null. It doesn't do anything. But the thing is, I can keep this profile in and can run it normally, and nothing happens. Only at compile time, it runs the function to here, which is doing nothing. And then I use the current profile, so that I don't have to comment this out and in when I want to profile and run the profiling off. Yeah, that's just my small trick here. And then I see, in this case, I just make it the local and say square root is this mass.square root. And here I access it in the loop. But I don't do any other calculation. I don't do the calculation, I just do the access. And then I use this in a test and call this two functions. And then when I run this local ref, then you can see a difference, what influence this has. Yeah? There's a difference. The question is, that doesn't matter for your case. Yeah? So if you do a lot of calculations anyway, then this little bit of reference might not be a problem. If you only reference, then there's might be important. It takes a bit longer here for some reason. Maybe I chose too big and it's too big an F. No, it's 10 million. Yeah, let it run. Still running. Maybe I shouldn't have used 10 million there, because this introduces a lot of overhead. It takes much longer. So I asked Robert Cohn about it. He said, yeah, this is an overhead maybe a factor of 1,000 slow or something. It's very slow, because you just want to measure, and this measuring introduces overhead. Yeah. And see, it's not a big difference here. Actually, it's not a big difference when you do this here. You do something like this. So now would be exercise time, but the problem is, if we do exercise, we won't get through. I thought there would be enough material, but I'm totally on the wrong side of this. So we have plenty of material. We just have 30 pages, we have so much more in only 1.5 hours. It's about, I don't know, 70 pages, so it's not even half. So this is an exercise, and the exercise in the handout is just show you. It's easy, so it's for you. If you be welcome to do it and ask me about it. Profiling, yeah. So if you go to the page 31. Yeah, this is an exercise here. This exercise, so you have these two functions. This is a very stupid function. It says insert 0. So I have an empty list. Yeah, I give it the default argument of 10,000 here. Empty list, and I go through the list, and every time in the loop, in this 10,000 times, I say insert 0, which is a very expensive operation in Python, because it has to rebuild the whole list 10,000 times. It has to get new memory 10,000 times, getting memory is pretty expensive. As opposed to the other function here, which is doing exactly the same thing, but it's doing append all the time, and in the end it just reverses the list in place. You get the same result, but it depends how big it is. It's much, much faster. And it's interesting to do an analysis so you can run through and make a nice graph with snake vision. You can see actually what's happened. Now I know I can tell you, but you can see for yourself, which is always good. But sometimes you think you know, but you don't. Yeah? What is it? And known knowns and unknown unknowns or something like this. At least you can measure and you can see what's going on here. Okay, this is a topic, profiling CPU, which is most of the time when people talk about profiling. But sometimes you want to profile also memory usage. And that's something I would like to show you now, how to profile memory usage. And there's a bunch of tools out there that you can use to do this. But there are two tools. One of them is Hippie, and the other one is Pimpler. They're very similar. The thing is, this Hippie only works in Python 2, and Pimpler works in Python 2 and 3. Therefore, probably I go for the second one. So I have pretty much the same scripts here, but what they do is pretty much the same. Maybe I start with a Pimpler first, and the Pimpler it actually used to be 3 projects that kind of came together, and I can even do it with Python 3 if you want. Yeah, now we're in Python 2. Save this Python 2. So they're very similar. The thing is, it can be nice sometimes if your results are not conclusive, use a second tool. If they're the same, they might be okay. If they're different, one of them is wrong. Yeah. Pimpler. Now you have this tool, and this one can give you a few things. Actually, from Pimpler import tracker. So IPython notebook is small enough to know that's import here, and then I say tr says tracker, it knows. So it's kind of looked already what's possible to import. So my memory tracker T would be tracker summary tracker. Different trackers, we just stick with the summary tracker, and I make an instance of my summary tracker. And now I can say my summary tracker print diff. And I can see print the difference. So there's not much difference to print yet. Here I can print it. This takes a little bit, so it's a bit maybe, yeah, because now I'm running an IPython notebook, and this typically IPython keeps a lot of things alive. So IPython in the background has a lot of lists about history and inputs and outputs, and there can be a lot of, if you look at OS modules, has like 700, 800 modules loaded. That's a lot of things going on. And now you see that's what's going on here. So I have about so many lists and so many strings and so many integers here. And this is pretty much, most of them is everything that's what the IPython notebook is doing. That's the difference what you have here. And this should be the baseline. There's always some baseline, but look at the unit, it's all kilobytes. It's not a lot. So when you measure memory, you cannot get very accurate results, but it gets, because when you have memory problems, you talk about at least megabytes or maybe even gigabytes problems and not a few bytes here and there. So that's pretty much the 0 here. So now if I create a big list, so if you're in Python 3, you better say list, in Python 2 wouldn't matter. So we say range, and what I have here, 1,000,000. So I always like to use the scientific notation because I don't want to count zeros, but a range needs to have an integer, so I convert the integers. So I created a big list, and now I reuse this command, the same thing as here. And I do this again, it takes a bit, and then you should see the difference. It takes a bit, has to go through all these things. So, still thinking about it. Yeah, okay. And now you see the difference. Up here we had 0.5 megabyte, or a little bit more then, yeah? And here now we have 22 megabytes and everything is ints. You see, I said 1,000,000. Why do I have less than 1,000,000 ints? Who knows this? Yeah. I think no integers are. Yes. The answer is the low integers are now no singles, that they are referenced. So the low integers between minus in CPy means -5 and 255. You can find this out. It's always good to import this get ref count 1. You see the 1 is referenced 5,000 times. The 0 is even more referenced. And that's why those lower little integers, they are referenced. There's the wrong thing. Ref count. 0 is 1 the most. Oh, 1 is more than, have more ones. Typically 0 as a winner here. But yeah. And if you say 1,000, then you see there's only 3 references. There's always one more. As soon as you use this get ref count, it creates another reference. So when you measure something, you influence the system. That's what this thing's doing. And there's one extra always in interactive and stuff. So, but it means essentially 1 reference. But you see now I have so many integers, 7 lists. So it's fewer lists. I don't know where the lists are gone. There must be some happen to the list. But it has so many integers. Fewer integers here and so many integers here. And when I delete my big list, it should be back. So you can see the difference between these things. No, I have to copy this here. It takes a bit. Now it should be back pretty much to 0. So, and I wrote a small tool. You see now we're pretty much back to 0. And that's much closer to 0. So if you do it again, I should get pretty close to 0. This measurement always has some overhead and sometimes going up and down a bit, but there's always a few bytes sitting here and there. So now it's only bytes, no kilobytes anymore. Yeah? And there's minus, which is obviously wrong. So there's some. Yeah? I don't think how minus bytes going to work. Yeah? So you shouldn't take it to find, but if you go down to a megabyte, then it's good enough. I wrote a few tools to do some measurements, and I'm going to show you something what you can do with measurements. This is memory size pimpler. Memory size. So I have a version for HPY, this HP here, HPY, and the pimpler, memory size pimpler. And I do pretty much the same thing. There are 2 different tools. And I use a few things here. I write my own decorator. Who wrote a decorator himself or herself? Nobody? Decorator 1? So a decorator is nothing mysterious. It's just a function that takes a function and does something with a function. A lot of functions there. And that's what it's doing here. So I do some imports, future import, you always should do this. Func tools, that helps us to make a nice decorator. We want to have a nice decorator. And some Python 3 thing. Interesting, I have a dictionary, which is called memory, which stores all the information I gather about the memory. And I write my decorator, and this is a 2-level decorator. This is a decorator that actually takes a function. And this is inside this function, I define a new function that's going to replace the original function. So if you want to be fancy, you call it function factory, because you make a new factory and a new function on the fly. Yeah. So I get a function here. And this wraps here makes it just nice. And here I get this args and keyword args, a bit magic. So this one actually catches all positional and keyword arguments. Yeah, another concept. And then I make my summary tracker. That's the whole thing. Here, now it's interesting. I make my summary tracker. Same thing we just did. I do 5 times and go to 0. So I get pretty close to 0, because when you do only once, there's still some rest. So that means I'm pretty much at 0. And then I call my function, and I try to return, and I use a try finally. So try finally is interesting, even though I say return, and typically after return, a function is finished. But when you're inside a try block, then the finally is guaranteed to be executed. So even though the return is here, this one will be executed first before you return. So I use a few tricks. So tricks, everything's official, there's no trick, it's just maybe things you don't do every day. And now, you see what I'm doing, I have a dictionary, and here I use a function, and the name is the name of the function. If you want to be nice, you would also put the module in there. So that's not really production grade yet, because if you have 3 functions, the same name, they would override each other. The module, maybe some other things. And then here I put this measure diff. I don't know where the parentheses come from, they're not necessary. But they don't hurt, yeah? Somehow, maybe change something. You can make as many parentheses as you want, it doesn't change the thing. So you measure diff again, and then you see the diff. Yeah? The nice thing is now I wrote this decorator once, so you can use it again and again and again. So writing decorator is a bit involved, but the nice thing you don't need to do is every day. The only thing you need to do is just to write this decorator for your function. So forget about it. If you have the script, you can use it. Just write it there and it's doing the right thing. So when I do this now, I run it, and it takes a bit. Yeah, it's going to print something when it's finished. So it takes a while, because now it runs a 4 million, makes this big list and doing this thing. And when it's finished, it's going to print the memory, which is a dictionary with my results, and I should be somewhere there. Takes a bit. Yeah. Okay, maybe I can talk a bit about the thing. So this, if you write a decorator, always your func tool wraps. This guarantees that your new function has the same name as a wrapped function, also has the same docstring. If you don't do this, you will lose a name in docstring, and all your functions will be called measure memory, which is not, if something goes wrong, you have exception, and you have 100 measure memory functions flying around, which is not really helpful. That's why I use func tool wraps. And now you see, I have this one, you see big memory, make big, it's the name of the function, yeah, and gives you this what I put in here. You see a list, this is integers, a list with the size in memory and integers with the size in memory. If you run the same thing in Python 3, this number will be the same, this will be bigger. Do you know why this is the case? Why integers are big on Python 3? Anybody? In Python 3, there's no longs anymore. Actually, integers became long. So in Python 2, it's the size. The size get size of now. Get size of an integer is 24. In Python 3, I can do it in Python 3. I can run a Python 3 cell here in my Python 2. But it starts a new program, that's I have to do the whole thing again. And I do the same thing here, but I have to print it out, otherwise it's the output. And you see this will be 4 bytes bigger. It will be 28. So they're a bit bigger. That's why the whole thing will be bigger. Yeah. So if we make a number really big, if we make it gigantic, it will be even bigger in terms of memory. That's why it will be a bit bigger. But this decorator can be pretty useful, because now you just decorate your function, and you can measure the size. And as I showed you before, you can even replace this decorator. If you don't want to take out 150 decorators in your code, replace it with a decorator that doesn't do anything. It just returns the original function. That means you have to only one place replace the decorator, and then you can keep it inside. And it doesn't cost any runtime, because the decorator is only applied at compile time once when you import the module, which is usually negligible. You don't need measures. It's just too short the time. Okay, this is one thing you can do with your Pimpler. Another example, I have this memory grows kind of thing. So Pimpler, growth of memory. Very similar concept. I do similar things, but now I measure. This one I decided not to use a decorator, but use a different technique. I use a helper function here, because I don't want to actually replace a function. It's similar, one helper, and this is a helper function that takes a function and the arguments. Again, this catches all the positional arguments and all the keyword arguments. And I do the same thing with my summary tracker. And then I call the function, and then I return it here. So actually here I don't care for the function result. I throw the function result away. Where the other one I just could do my normal calculations, and the memory measurement was a side effect. Here the memory measurement is a whole thing. And the function is the side effect. I don't want to do it. Yeah. And I have this small helper. And now I have a test, and I write 2 functions here. Big, which just returns a range. I see. If you're in Python 3, you would want to put a list around to make it nice, because in Python, yeah, no, it's okay. Be careful. Yeah, this one the range object is not really a list, it's just a range object which doesn't take any memory actually. But grow is something different, but it doesn't really matter because you return it, so the function doesn't change. And here, if you don't assign anything to the function call, which I don't. Yeah, if you throw it away, there won't be any memory. But here's different. You generate a list here and append something to a list on a global list, because I make a global list and I change the global list. This is in general not good style to work on a global list, but you still can do it. And you will see the difference because I changed the global list. And then the thing is different. See, I can put in the function here, my check memory function, that's this one. And the first argument is this function, and then the arguments. Yeah? This is a function make big and the size. So the number is the size. Maybe I should call it number. And the grow is this function and the size. This is a different approach, which is nice because now I can write a loop and go through all my modules and collect all the functions and can run them through here. It's a different approach than the decorator, maybe has a different purpose. And when I run it, it takes a while, and you can see the memory usage of this thing. So it takes a while always to measure the memory. So it doesn't come back. It takes a bit more time. Yeah. So especially when I run it inside here, inside the star means it's always running. Sometimes when you make a mistake or see a star, and the trick would be, you see you go to kernel, if you interrupt, it should interrupt it. It's like pressing Control-C. Sometimes interrupt doesn't work, then you have to restart the kernel. When you restart the kernel, you lose everything in the kernel. Okay, what's a kernel? I'm running in the client in my notebook, which just saves everything in the client in an IPython notebook file. And the kernel is other program that's a server you connect to. So even if you kill the kernel, you keep the notebook, you don't lose the notebook. And the notebook is saved automatically every minute or two. You can change the save interval actually in the configuration file. And that wouldn't be a problem. So even this hangs for some reason. Maybe I chose too big a number here or something. I'm not sure. No, it's 1,000,000. That's there. Finished. So now you see, if you say make big, it's actually empty, it's nothing. And here you see this, the size you have is pretty much the same numbers as before, because I use the same size at least. So you can see the difference. Okay, now you see, okay, if I program it this way, or program it this way, what's the impact on the memory? Yeah, of course, it depends very much on a use case, and you have to, those numbers can be misinterpreted very easily. You have to be very careful what you're measuring. I think that's my main message. When you measure something, you have to ask twice, can it be correct, and is this the right approach? Maybe try a different approach to get to the same result. Yeah, because if you measure something wrong, you try to optimize it, it is not really going to work because there's no way to see any progress. If you measure something that's not there, it won't be very helpful. Okay, let's go to the command line. I want to show you something that's Python 2.7, 2.3 also. Measuring, I want to show you the measuring this list thing. Is this a list? It's a list. Check memory. Just to show what's next in my schedule. Yeah, the size of thing. The list grows. How they're interesting when you use append with a list, what happens? So when you say append, Python has to change the size of the list. But it doesn't do like adds a little bit to a list and a little bit. It takes quite a bit more and puts something in. This can be very nicely visualized here using this Pimpler list grows. So if I do this, and I use actually matplotlib to visualize things, so it takes a bit to do the measurement, and I plot something. And I use 3 different. Maybe I'll show you the function first. Otherwise, it doesn't make sense yet what those pictures mean. Okay, let's have a look at this thing first. Load Pimpler list growth, and you see how this works. So this is actually what it's doing here. I have this list memory. I get the length of a list. And then I get a function. So this one here, this flat size is a function. Where does it come from? There's 2 different things. One is Pimpler as size of module and has a function as size of or flat size. They do different things. Because when you measure the size of an object like a list, when you do it in normal Python with this, so this get size of, it measures only the size of a list, and every element has the same size. It's just a pointer. 8 bytes. No matter what's in there. If a false or an integer or whatever, doesn't matter. It's just a pointer. This pimpler offers you also to measure the elements inside recursively, which is sometimes what you want. And you get a different result. And that's what I'm doing here. I just can kind of, what's called a callback here. I get, or dependency injection, what I want to call it. I have a function here which I'm using, and I go through. I have this my list, and I calculate the memory, which is actually this function here, and I put the list in, and then I just go through and add this to the list for all elements in range of the length. So if I put a million, it starts a million measurements, and put it in, and you see how the things are growing, and you can see what it's doing, and returns the memory. Yeah? So you get a list with all these steps and memory after every append, how the memory grows after every append. And I do this for 3 different ones, so flat size, A size off, and this get size off. And down here, this is just this matplotlib code that's actually plotting the matplotlib. And actually, I could have done it from here. You can do it in, say, matplotlib inline, but doing it from here. So the first one, see, you get something like this. And it's very nice. You see the allocation. You see how the memory is growing. It grows, and then it stays for a while. That means the list is like this, and Python puts like about 50% or so more, gets more space, and then it can fill in the space and reaches the end and gets another chunk. So that means you minimize the number of allocations. Allocations are expensive. If you do a lot of allocations, it's getting very slow. So you use up more memory, but you make it faster. And that's a typical trade-off. You can always put more memory in machine, but making the processor faster is pretty hard. They're pretty at the end now. They don't get so much faster, but you can triple the memory of the machine. That's not a big deal. And though Python uses more memory for speed. And this would be pretty much the other exercise also with the insert and this append has the same effect. And this is now this A size, and the next picture would be the flat size thing. And it will be different. It takes a few seconds. You see now, the steps are much less because now I also measure the size of the integers. You see, every time, every step, one more integer. The integer also takes space. That's why it's kind of pretty much straight. And this is just this jump where it gets more space. But in the meantime, the integers are measured also. The other one was like this, and this is like this. And the last one is the sysget ref size, which is pretty much the same thing as the A size, same step function. But it's interesting to have this knowledge that makes reasoning easier. I think when you see a picture, at least for me, if I see a picture, I can remember the staircase here, then having somebody give you, there's an equation, you can calculate this, but you don't remember the equation. You can always remember staircase. Okay. This is something you can do here, and have another one, which actually, this last one is using this, you see how many allocations I need, list allocation steps, it's called. Nice tool. What's the name of the function? List allocation. Yeah. So this one counts how many of those staircases you actually have. Yeah. So it's the same thing here with this function, but instead of actually drawing the staircase, I just count how many times it switches. Now, if every time the size changes here, so if the old size minus new size is more than the in size, I increment it by a step. That's pretty much what I'm doing. And then I run it for different numbers, starting from 10 to 10 million. And you see here, if I have 10 appends, I have 3 allocations. If I have 100 appends, I have 10 allocations, and so on. You see it's getting less. When you have 10 million, it's only like 104 allocations, which is very little. Yeah? If you have 100 million allocations, it can take an hour or 2 or something. I don't know, even longer. And you see this is the same as here. Get size of and A size of this has the same effect. There's no difference. Essentially the same thing what it's doing. But you can prove it. So this gives you this is exactly the same information as in the staircase. Yeah? But as numbers, not as a staircase. But it can be interesting. Good.
So I have a quick question.
Yeah.
So how do I mean, I look at something like this and I'm not necessarily sure what's good and what's bad because you made the statement about the trade-off memory versus allocations, right? So I'm not sure that 27 allocations versus 10 is any better unless I wrap it around, okay, what's the memory usage and then what's the speed altogether. So I guess I'm failing to see how this would be used in a real world context, I guess.
The question is how it's going to be used in real world context. No, you don't compare 10 to 27, you could compare 1,000 to 27.
Okay.
You compare 10 million to 104.
So it's less allocations, but theoretically you're at any given point in time with that 100,000 to 104 allocations, you're using more memory on any given step because it's doing a big step, to do a big allocation because it knows it's going to need that much more space. So I don't know if I'm fully grasping how this helps me make a decision because there are other things that need to be taken into account, like memory usage.
Yeah, so the question how to make a decision. No, this is not a question how to make a decision. Now you see how Python works. It's important. You can visualize how Python works. When you use a list with append, that's what it's doing. You cannot change it. But it has a good reason. People did it this way for some good reason because in most use cases, that's the right thing to do. If you have a different use case, you have to use a different data structure. Yeah, so you always use a bit more memory. So dictionaries use even more memory. So dictionaries only fill 1/3 to 2/3, something like this, and then you have to make it bigger. And because if they fill it, the lookup times will go up. Yeah. So this is something here. This is pretty much most of the time you use a bit more memory. And because if you have a list, you want to have it has to be one big block of memory because you can address every element by indexing. Yeah. So and if you do this, you have to allocate the whole thing again and again. You always want to have a full one anyway, so it makes better do one big one, and you're done for a while, and then you do another one. That's the logic behind it, pretty much. The thing is, you cannot change it. If you want to change it, you have to use a different data structure, not this built-in list. You have to make your own or use one of these collections data structures. There are different data structures that might be different. Or if you really are conscious about memory, use NumPy arrays. Because here, every integer is 24 bytes. In NumPy, you can have 60-bit integers you want. 16-bit integers, yeah, and you can much less memory if a number is not big. And then would be about NumPy arrays are static. You cannot change them anyway without making a new one. So that would be another alternative. It's just give you some nice, because I like this graph because you can see what's going on. Yeah, and you can maybe you can take advantage of this one way or the other. Depends very much on your problem. At least you know. If it helps you, it's a different question. If it's good for real world code, I don't know, but I know what's going on. Maybe I cannot change it, but at least I know what's going on, and I don't need to spend time trying to change it if I cannot change it if I want to use a built-in list. Maybe that's. I hope that answers the question. Anna. Sure. Okay, good. And now there's another way of measuring memory. There are some other tools. I said this CP is would be another tool, and the other one is it's a line profiler. It's called memory profiler, which works similar to the line profiler. And again, you can use this decorator profile. It has the same name. Oh, yeah, I didn't put the function name here. Use memory. Use mem. Yeah, use mem. So this is just see now I can put this profile decorator here, and I can similarly to using this current prof for CPU time line by line. Now I can do memory line by line. This has a few problems. I found a few things that don't make too much sense here. And actually, you can do it from here. Memit doesn't work. Load extension. I hope it works. I'm not sure. I didn't test it here. Yeah, worked. Now maybe the memit should be here. Yeah, now it's there. So this typically it's the same thing for the snake list. So you load an extension, And IPython notebook notes, of course, memory profiler is defined to have an extension. Now I can use it from here, and I should be able to do something like this and run so this memory thing. See if I run this one, what comes out here. The profile, it doesn't work the way I want it. This. So if you use a double % sign, typically you can use a whole cell. Now I'm just trying it out. No, it doesn't work. So run from the command line, so it doesn't work the way I expected it. But nevertheless, you can run from the command line, and I can say Python minus memory. So I use a module, again, the same approach we used before. Memory profiler, which would be the same thing as importing this thing. And then use memory. And it takes a while, and it should give me a breakdown of the memory usage. And then you can see where memory is allocated. And the thing in the background using some system tools to measure the memory. And this can be a little bit sometimes off. I think especially on the Mac, because Mac is doing something with the memory and compressing memory and doing stuff, and that might not play well with the measurement. So I'm not sure. Sometimes you get very strange results at this place. So that takes a bit. That's pretty slow because it has to do all those measurements, has to wait in between those, has to take those lines apart and wait and measure the memory. So it takes a few seconds. Then you get a breakdown. I hope I didn't make the number too big. No, it's 1 million. Because I used to have like 2 orders of magnitude more, which is not going to work. Because it takes too long. Yeah, let it run, and we can go on and just look at the result as soon as it's done. So this memory profiler has a few more things you can do. So actually, if you don't know what memory is doing, you can use question mark. It tells you what to do. Should be some usage. Yeah, statement. So you have to put a statement that would measure the memory of for the statement, and then you cannot put this decorator. You don't have to put a decorator, including timeout. So if it takes too long, you can give it a timeout. It doesn't go on forever. And there's some examples here. So it's generating in 10 million zeros with NumPy costs you about 76 megabytes. Yeah, and ones would be about, it's only 1 million, so it's a tenth of it. Yeah. What is minus R? It repeats 10 times. So it's not only once, it repeats it 10 times. It's still running. Yeah, and you can also do a few things. You can import it and actually can measure the usage of this IPython notebook here. So you say from memory profiler import memory usage. And then I can say memory over time, make it shorter, memory over time, but I have here memory usage, and just you provide a few arguments, and it's going to memory. So, and you can provide the interval in interval, yeah, half a second, and the timeout of 3, how long it supposed to work. Timeout 3, and the first one is just. And it gives you, and it takes a while for 3 seconds, and it shows you how the memory developed over this time. So you can kind of continuously monitor. Now it should be there, and you see that's the memory, and it doesn't change much because not much is happening. If something else would be happening, yeah.
Does it measure only the memory of that Python kernel or of the whole system?
The Python kernel, the process that's running here, it's measuring the Python kernel. Yeah, it's not a notebook. Yeah, the notebook is a JavaScript that has nothing to do with it. It uses way more than 13 megabytes. Yeah, maybe 10 times or 100 times as much. Yeah, now you see I get a breakdown here, and this breaking down you see that can be interesting. How much memory? See, when I make a list, it uses memory, and when I use this one is sum, and I'm not using it. This one makes a list inside here. Is a list comprehension, and you make a list of so many numbers, and then you sum it. Here, I do generate expression. Actually, there's normal parentheses here, but you can skip them. You can even leave them out. And then you don't generate a list, you just sum it up immediately. And you see, this shouldn't be minus. It shouldn't gain anything, but obviously the operating system is still cleaning something in between. It frees the memory from before, I guess. I'm guessing it's still minus. And then when I make squares, you have another memory. Yeah, because here it allocates 30, and here it allocates only 10. That doesn't make a lot of sense. It should be the same, because here, if you sum something on here, actually you store the whole list. Here you create a list and sum it up and throw it away. And you use more memory than here where you keep the list. It doesn't make too much sense. So the tool gives you some numbers, but at least, I don't know, maybe if you have a Linux system, you might get some more consistent numbers.
You end up with the same sum memory usage. So because of the delta, it's weird, but you end up with still, so line number 11, you have 67 megabytes allocated. And line 14, you have something pretty close. So if it allocates only 9, it ends up with something in the same ballpark.
Yeah, this is kind of, okay. This is here, 30 by 30 is 66. Minus 6, so this at least this is consistent. Yeah, so this is the memory, the total memory, and this is the difference, and they shouldn't add up at least. Otherwise, it wouldn't make any sense. At least you can check this one. Otherwise, you have a problem with the measurement. But it's kind of tricky. When you delete something, at least it's negative here. You freeze the memory at this place, and here I calculate the string. Yeah, this one can be allocated in one thing, and then delete it. And it doesn't free anything. Even if I delete it, you don't see anything freed. It's the same. Yeah, I don't know why. And the return doesn't free anything here. Even though all these locals could go out of scope because I return an integer and all the things should go away. But it's not happening here. And because Python's reference counting, you should say, okay, there's no reference anymore. Now it's time to garbage collect the stuff. So it's a little bit tricky. It's there, but your mileage will vary, so the output is maybe not that clear. Good. This concludes this memory measurement. I have an exercise again, which would be maybe interesting to do. But I have a few more topics that maybe you're interested, because I have a few more things about this. There are some small snippets, recipes, how to start saving. This used to be this tutorial had a second part where I start going to a little bit PyPy and there's some NumPy things and this, but it's getting too much, and then you want to use Cython and you want to use Numba and you want to use all kinds of things that you can do, and it takes a long time. And I rather maybe touch this a bit more here. And I can show you maybe now a few more things that you can do to maybe save some time or memory or both, and show you some patterns or anti-patterns if you're interested. Just a few more minutes. Maybe you're familiar with some of them already. So one anti-pattern would be doing something like, I have a string, and then I have 4x in range, or x range, whatever, 4x in range, and you do this. S plus equals. Something like this. Yeah, this gives you now a string with 100 A's. Yeah, should be, you can even print it out. This is an anti-pattern. You know, anybody knows why this is an anti-pattern? Actually, in CPython it's not too bad. They optimized it away, actually. But if you use it, if you do this in PyPy, which is by far the more faster version, and you do it for not 100 but 100 million, that will take you a day or so to do this. This is because strings are immutable. So you cannot change a string. Yeah, you cannot change a string. So every time you do this, actually, you would need to create a new string. That means do new allocation, same problem again. So they have some optimization, but it basically would mean to create a new string. And if you use PyPy, you see a big, big hit on the time if you do this. You never know. Some people want to use PyPy with your program to make it faster. And you do something like this and you get it much slower because you don't even realize if you do it with CPython, that's so much. Enough of that. So anybody knows what the solution for this problem would be? So the solution would be a list. So you say result is an empty list. And then you have the same loop for x in range 100. And you say result append. It doesn't append yet, I haven't executed cell. A doesn't have to be A, it can be any kind of string from somewhere. So the problem is now, of course, my result is now a list, and I want a string, and the typical way to do it is use join. So I say, okay, join nothing, a string of a length 0, in between my result. And then you get your 100 A's. And if you do this timing, then you should see you can do time it from in here. Maybe I didn't even mention this one. You can do the time it, and then now it's running it many times, and you can see how long it takes to do this. So that's time it. I see it's doing it 3 times and doing so many loops that takes those 100,000 loops takes about a second. And then takes the fastest loop for one loop, the 100,000 for one loop, and it's about 8-9 microseconds here. And I can do the same thing here. So I have to use the double % because I want to have the whole cell, and this one now it's a bit slower actually here in this case. So it's not a good example. At first it's very short with 100, and second it's optimized. So if you do the same thing in PyPy and run this in PyPy. So this is a built-in, this time it is now specific to the IPython notebook. If you want to do it by hand, which is sometimes not a bad idea. So you have to import the timeit module itself. Import timeit, which is a timeit module. And as I said, with timeit dot default timer, you get a timestamp. So it might be, in a different operating system, might be a different number, but it doesn't really matter because most of the time you're just interested in the difference. So you have a start and an end. So that's what you do now. You just put the start and end around here. You say start is this, and then you have an end. So, because I do this not without a reason, because if you want to, you can live with this IPython notebook pretty much. And so, and you can do something like this, and then you say print default timer minus start. This gives you the time it takes to do this. And this parentheses should go there or not there. So, and now you see the time. And now when you do this, you can also use, say, PyPy, and you kind of run the whole thing in PyPy, which I have installed. It's much faster. You can see the time is much faster. And of course now this it's a little bit not so nice because this 100 is hardwired. Call it n. At least put it here, so it's a little bit outside. Because this is a totally new process, and the PyPy doesn't have any access. So when I do the same thing, I fortify my code here with my PyPy, my print time So you see now, this time is quite a bit bigger than this time already. Yeah, there's -4 and -5. And now if I go up, and let's say I got a 10,000, or if you want, I prefer always this one because it's easier to write. So it's 10,000, and then you have to be very careful with the numbers, otherwise it takes ages here. So 10,000. Yeah, I have to put n here. That's a good idea. You see, now it's, I can delete those lines, so dd deletes itself, escape dd. Okay, and now you can compare this number. It's here, this is 0.02, 0.01, so it's a difference already. And if I go this up, to be careful, 20,000, 20,000. Yeah, you see the difference now. It's only one order of magnitude different already. And 30,000. So you see how this differs. Now, if you write a program, you can write a loop. But let's go to 5. And now you're in a quarter of a second, and here you won't see a big difference. Stays pretty much the same. And if I go even one higher, this might take a while. Now it takes a while. It takes more than a second. And if I do the same thing here, now I'm an order of magnitude faster already. And if you keep this, it is getting more and more apart. Yeah? I remember doing this in command, I was much slower. I don't know why it's so much faster from here. The difference was much bigger. So this is one of those anti-patterns. So there's a bunch of these that might. The problem is if you test everything with small structures, it's fine. You won't see a difference. Because the relative difference is not that big, and you won't see anything that's of importance. But if things get big, that's when it gets interesting. Then you might see a big difference. This pattern we'll see again and again and again. So you need to find, if you want to test things for memory or speed, you find to have data structures which are roughly the same size as your production set to get some useful numbers about how fast things will be. Yeah? If you test everything very small, then you won't see anything. Because when you multiply, you tend to think linear. You tend to think 10 times as big, 10 times as long. It might be 1,000 times as long. So, and that's a problem if it's not linear, and then things go wrong.
So that's all because of the immutable string.
Yes. So the reason for this is the string is immutable, so you cannot change the string. So plus equal changes the string. You can.
What about just a times?
And that would be the fastest. If you know this, that would be by far the fastest. A times 100 would be the fastest, because then you know everything at once. But the A is just an example. So assume you don't have A, you get a different string every time from somewhere. Yeah, because this would be the fastest, because this knows exactly how much memory you need. You have one allocation, you put everything in. That's it. That's very easy. Yeah, but if you don't know and the string is changing in size and you get different strings and you want to put them all together, yeah, it's an artificial example. But since it's artificial, it's good enough because you can abstract all the other things away and you can see the core of the problem. And the problem is, if you have it in real life, you might have this problem, but you might not recognize it somewhere in there. You have all these variables, and you might not even realize that there are strings at this time or something, or that something could be involved with strings or so, and something goes on. This can happen. There's the same problem underneath somewhere, but you don't see the pattern yet. Yeah? But if you know it's there, you might have the feeling that feels like maybe it's somewhere, and then if you look for it, you might find something. Yeah? So especially if you didn't write a library, it's from somebody else, and this was written for small cases, use it for much bigger cases, the thing might explode somewhere. If you write it yourself, the chance is much higher that you find it. Somebody else wrote it, and you might not understand fully what's going on. And then it might be helpful to at least have one way of some idea what could happen. You need a hypothesis, don't you? You need a hypothesis. You need to know what it could be. Okay, the next thing is generator expression and list comprehension. Who knows what a general expression is? Most people, yeah? So a list comprehension is this nice thing, which the name comes from Haskell. So now I use range. In Python 2, I should use xrange, and in in Python 3, it's range. That's why I like to do something like this, which I did for now. So because range generates a list in Python 2, but only a range object in Python 3, which doesn't consume any memory. It's just the range object itself, but if it's bigger, doesn't consume more memory. So that's I can use something like this. Probably you should use a library that factors this out. And now I say 10. So this one actually produces a list in memory. If you want a list, then that's what you want. But if you only want to have the sum, as I did before, then you're not actually interested in this intermediate list. But nevertheless, Python is generating this intermediate list. It makes the sum of the list and throws it away. You can, instead of using a list, you can use a general expression, which is just changing the square brackets in normal parentheses, and it's doing the same thing. But it doesn't generate the intermediate list, which is no problem at all for 10 numbers, because there's no big impact. What's this? No big impact on it. But if this is big, so here, you can put in a number as big as you want. There's no limit. In Python 2, it's a limit. It's the biggest integer. In Python 3, there's no limit, because you can use a long. It takes very long, but it works. If you do something like this, you get a memory error sooner or later, because you use up all the memory. Or the worst thing is, you use so much memory and start swapping, and it's getting so slow that it never recovers. You do anything in terms of machine. Yeah? And you can always use time it now to measure how long things take. Yeah. You see, they always want the new time it wants when there are so big differences between those timing steps, which is especially true when things are small. You see, there's no big difference. But I can set n. Now, this time it will access n from outside. So I have the same n, which is nice. So I can just use n here, there. And there might be a difference. Yeah. Not much, but it's 1 loop and 10 loops, a little bit different. I can try a bit more, will take a while. But as soon as it gets very big, then you might almost have to get a jump, because then there's not enough memory anymore to put it in. And it tries to get memory from all the places, rearranges memory, it takes time. Yeah. Why is it so fast? Did I execute it? Yeah. Maybe it's this. I want to make my point, and it doesn't make my point. Yeah. At least it lets memory, so you can try. I have experience, if you do this in Windows, then you will find the place where we have a really big difference. Because memory management is largely dependent on the operating system, how they do it. So even if you're on Linux, you might see some different effects someplace.
Both of them are using range, because we defined range earlier. So both of them are using X-ray.
That's fine. That's what I want. But here I still generate the intermediate list. So if you measure... Yeah, because I use the parentheses here. That's why I use a range. Otherwise, it would be unfair. If I use normal range, actually I use X range here. Yeah, so that's okay. That's what I want. So they have to be. Otherwise, if you generate the range here, then you can do generate expression as you want. You don't gain anything. You have to allocate memory. Yeah, there are some cases where actually they are creating the intermediate list is faster than. There are sometimes some places where it's not always that it's faster, but this is the nice thing, there's no limit how big it is. Even it runs overnight, but it runs. And this one, by the way, this will run overnight and this won't. So that's another thing. Those small things can matter, and sometimes makes sense to think about it. Noch 7 Minuten. 7 minutes left, so not much. Okay, I have a few more things. What's here? I have something about data structures, and you can read through it. It's pretty much so. We haven't finished the whole thing, but I think my main focus was the measuring anyway of those things, which is important. And maybe I just sum up, and then if you want ask more questions, I don't want to start a new topic, because I've forgotten. Very important announcements. There are still lightning talks. You still can sign up for a lightning talk. Maybe you know what lightning talk is? It's like 5 minutes.
It's in that room, and did you sign up on the third board? Did you sign up?
I know I have to find a topic first there. And so it's 5 minutes, no questions, and the 5 minutes are sharp, and you can talk about anything. Most likely something about Python and maybe big data or PyData. What else? I should say something else. Valentin said something. I've forgotten. There was an incident that people just unplugged the camera and plugged in their own charger, which is not a good idea because a camera needs energy to run. And if you unplug it, it doesn't have energy to run, so you should not do this. Okay, now my summary. The measurement is very important. You should spend a bit more time on measurement, because if you don't measure, all this optimization thing might go the wrong way. So you need to measure first to find out if you have a problem. If yes, where the problem is, and then can build a strategy based on this. If you just try random things, this is faster than this, and I have to use Fortran because I have to be fast, it might not be the best answer. You might spend a lot of time and end up with no gains. Things might get even slower. Using multiprocessing in the wrong way can make things slower, for instance. So because especially in Python, multiprocessing means you have to start several processes, communicate to these processes, and if you have a NumPy array and chop it in part and send those parts of NumPy array somewhere to calculation, send it back, very often it gets slower because this serialization sending back and forth won't help. But if you measure things before, then you know where the problem is, and then you can try something at least, because it's you said you have to make it faster, and then you can try things, and you should measure along other things. And I hope I've showed you a few approaches in the standard library, this C profile. And some nice tools like the snake quiz, which is pretty interesting. This gives you some pictures, gives you some feeling. And if you use it for a while, you also get a feeling what the circles and arcs mean. And you see where you see okay, this is a big arc. It makes sense to do something in this function. And I don't have to fiddle around with all the small pieces here and there. I just go with a big one. Yeah, that's important. The same thing with memory. You can measure memory with these tools. This Pimpler gives you some useful numbers, and you can write some tools, as I showed you. So you can, the advantage of writing your own tool, you can adapt the tool to your need. So you can write your own decorator, and then the nice thing, very often, if you're smart enough, you can keep the decorator in your code and turn it off totally in production, without one switch, without any overhead, and turn it on again. And you could even say, okay, automatically on a weekend it turns on itself, it measures, and on the weekend you have a lot of load that turns off because it's overhead. Or something. So there's something, if whatever fits with the need, you can do something, writing your own tools. And then do some visualization, and using a little bit Matplotlib is not that difficult to make some staircases. And those staircases might be useful because they give you some insight what actually goes on in the background. It's just an example. And your use case will be different, but maybe you can apply some of those principles. And you should always be cautious when you measure something and think about, could this be right? And if you're not sure, try a different method. Use some operating system things, just write this extra process, use a task manager, whatever you have to measure the memory and stuff like this. Chop it apart and see if it gives the same result as your tool. Your tool might be wrong, or you might be using the tool in the wrong way. Who knows? That's always the thing. So in the end, it boils down to common sense, as always is, and you have to apply common sense, but it makes sense. And you have a lot of tools and use those tools. People thought through and pretty much found problems, and you don't have to make the same mistakes again. You will make enough mistakes when you do things anyway. And we have 3 minutes for questions, and I hope you got something out of the tutorial. There's way more material in here, so I thought it wouldn't be enough, but it's plenty. Way more material there. And also, if you're interested, we also teach courses. If you haven't anything, you can take some colorful paper here, some flyers. So we teach Python courses, not only optimization, Python from beginning to advanced. So if you want to run your own decorators or meta classes, if you like, we teach this also, or courses for scientists. So if you have interest, you can reach me. So I will now plug maybe some questions. So that seems like I explained everything to them. Yeah?
Can anybody come to your Python Academy, or is it just for companies or groups of people?
It's open. So we have open courses mainly in Leipzig, but also sometimes in other places in Europe. And the individuals are welcome. but we also do in-house. So if you have a company institute, you say we have 10 people, they want to do something, then we also do customized courses. If we want to have a little bit from this topic and from there, then we put something together and even make some new topics if you really need to have special needs. Yeah.
You had said that a lot of this depends upon the context of the data that's actually running through the actual function.
Yeah.
Just in basic, debugging, you always look for those edge cases and how to test those edge cases. But I was wondering if you could give a little insight as to how you ensure that that range of data is the right range of data to be profiling. Are you sampling? How are you doing that kind of work?
Tough question. The question is, what size of data is the right size of data to measure? And the question, the question is appropriate. No, I don't know. It has to be something that matches what you want to do with the data. So that's really difficult. You need the context. And if it runs with 10 times the size of data you can expect, then you're probably on the safe side. I'm not sure. So I cannot give you a good general answer. I would need to probably look at the case, what you want to do and how things could develop. Maybe the problem is if you have a system that can grow in all directions, kind of over-engineered, because you have to provision for all kinds of cases that might never happen. Right. And the other one, if you make it too narrow, so that's something that's very tough. Yeah, the Java engineering has this tendency to over-engineer things. They make it this case another adapter, another thing, and can do everything, and then you don't need to do something totally different. Yeah, who knows? Sometimes you have the system that developed somehow. You have the CGI script that's still running. It's 15 years old, still doing things, and it's totally over its head, but it's still running because nobody did something else and nobody ever thought this was done. It was supposed to be afternoon hack and 15 years still alive. And it's very difficult to predict what's going to happen, especially in the future or something. And so it's not that easy to say, and you cannot give this the answer. You have to look at the use case, and then you have to be lucky things develop the way you expect. Yeah. So I cannot say I know how things. There's no real general solution for this. Sorry. Okay, let's go to the lightning talks.